The content presented is offered through Statistica Hub. Your support sustains Statistica Hub's commitment to providing high-quality educational resources for free through its open course programs. Explore additional courses on the Statistica Hub platform at www.statisticahub.com.
Hello everybody, welcome to the lecture 5 of Bayesian Inference. So in this lecture we are going to see some basic foundations, Bayesian procedures, Bayes theorems and all these things. So starting with the Bayesian framework, I'd like to start with like a change. What is a change? As we know that in our lives we usually go through with some changes. Changing is, you can say, simply part of the life. Everybody changes their mind. Like we likely even change our mind at the last minute of making some decisions. So when we are talking about the changes, we are actually trying to say that we continuously update our knowledge as we gain some life experiences and as we gain some information, as we collect some data regarding any experiment. So by changing, by gaining experiences, by gaining more and more data, we are updating our knowledge about that particular thing. That's what we do in the Bayesian. Now, yeah, let's try to look at with some example. Oh, yeah. Yeah, Bayesian Foundation. To understand that how does it work and what we will encounter in these types of scenarios, in the Bayesian scenarios, let's take a very simple example. Let's say, let's say, let's say, that's an honest answer that I like Indian food. So I like to go visit some Indian restaurant. And let's say I'm considering that there is a nearby new Indian restaurant that has opened recently, and I have seen the online rating that this new Indian restaurant that has opened, it has a 5-star online rating. Okay, we are saying that this restaurant has a 5-star online rating. Now I'm assuming by its rating that it will be having some good delicious food. Okay, so what can we say? That let's say I want to try this food, and for this I am going to visit this restaurant. So let's say I have visited this restaurant, I've ordered my favorite dish. It can be anything. Okay, we ordered our favorite dish, and then we, after eating that dish, let's say I don't like it that much. Okay, we don't like it. So we are expecting it too much that it is going to be a good dish because it is a 5-star rating restaurant, but it doesn't come out very good. So from this knowledge that you are having, that you don't like this your dish, you are updating your knowledge that it's not a 5-star online rating restaurant, it's a 3-star restaurant. You have said this because you don't like your dish. Then after this, what you do, you're going to give it a second chance. You're going to give restaurant second chance, let's say, because you might be thinking that like there might be some problem on that particular day, there might be something uh, you unusual about that dish that might have happened. So you are saying, let's just give it another shot, and I'm going to visit again in this restaurant. So this is your visit 1. Then on your visit 2, you have again ordered your favorite dish. Then favorite dish. Then on this second visit, you like the dish. You like dish. Okay. Then you have said, oh, I like it. So let's update our star of this restaurant. I'm now going to give it a 4-star. Okay, it as a 4-star. Now, as you continue to visit the restaurant, what you are doing, you are collecting some edible data. Okay, what we are doing, we are collecting some edible data, and then by that data we are updating our knowledge. We are updating our knowledge or information each time. Each time. How? Let's see it. What was the incoming information? At first case, you're having the first information that there is a very beautiful restaurant that has opened recently and it is having a 5-star online rating on it. That is your incoming information. Then you said, let's visit it. And you have visited it and you have collected some data regarding it. In your first visit, you don't like the restaurant. That means you're not a good dish. Okay, so that is the data that you have collected. Now, after this data that you have collected, you have updated your information. You have updated your information that it's not a 5-star restaurant, it's a 3-star restaurant. Then in the second visit, you again visit and you collect some edible data. Now you are saying that it's a good dish. Okay, you like it. Now after collecting some more data, that's a good dish, you are again updating your knowledge about updating information that I can raise up the rating to 4-star restaurant. That it's a 4-star restaurant. So as you are going to continuously visit this restaurant, you are updating our knowledge and gets to understand it better, that whether it's a 5-star, 3-star. So by change, when I usually start, I say that change. That's the change that we are seeing. We are collecting the data and we are gathering the information, and then we are updating our information as we are collecting the data. Okay, as you can do more and more visits, you'll be getting more experiences and you are updating your information. Now let's see this point in some other scenarios, that this is actually the natural Bayesian knowledge building process. That's what we do in the Bayesian knowledge building process. Okay, so in this process we are acknowledging our perceptions using the data to update our knowledge and then repeating it. As we will be repeating, we are continuously updating our knowledge. Now we can apply this same scenario as we have done this in example of restaurant. We can apply this same scenario when we are doing some research kind of thing. So let's say, if you are doing any kind of research, so whenever you are seeing in these types of problem, where you are having a prior information, initial information, this thing that you have seen, incoming information, this is your prior information. This is your prior information, and that is the data that you are collecting. And then after collecting the data, that the updated information is said to be the posterior information. Posterior information. Okay, so whenever you are having some kind of prior information relating to any experiment or any research question, for example, if you are a political scientist, then you might be interested in voting patterns. So you will be having some past years data, like you can do some research on it. You can use that data to make some interpretations. If you are an environmental scientist, then you must be like interested in climate changes data, right? So whenever we can use some past year data, I have the available information, then I basically you will utilize that information. Otherwise, what's the use of it, right? So let's see this. Whenever so in these types of problems, we have some information based on based on uh, previous research and experience. And this information is said to be the prior information. Okay, and by using this prior information and new data, okay, by using this prior information and new data that we are collecting, we update our information, and that is said to be the posterior. Okay, so we will be having prior, we'll collect some data corresponding to it, we'll update our prior to posterior. Okay, then we will, let's say, again collect some new data, then we are up, then this is my prior, now I'm again updating our knowledge, then I'm again getting a posterior. So you will continually do this procedure for updating the knowledge. Now you must have heard these two terms, that is Bayesian and frequentist analysis. Bayesian and frequentist analysis. Now we have heard, like in the starting lectures, I've already discussed that what is a frequentist approach is. So talking about these two scenarios that we usually hear, the Bayesian and frequentist approach, they actually share a common goal. They both do the same thing. And what's that thing? They use the data to fit the model, they make the predictions, they evaluate hypotheses. So the basically the goal of them is just to understand about the data. Both of them use the same thing, interpretation of the data, making the prediction, solving hypothesis. But the difference, our goal here is not to take the sides that whether Bayesian is better, whether frequentist is better. They both are good, they both are good, but the thing is, we are not to take the sides. The only thing is to understand what is the key difference in the logic behind each of their approach. Okay, the key difference is to understand the logic behind their approaches and interpretation. That is very important. Interpretation of Bayesian and frequentist analysis. Right? Let's take a simple example. So let's say when we are flipping a coin, we always say that the probability of head is 0.5. Now, how do you interpret this? How do you interpret this? Okay, like some would say that it is an equally likely thing, and other, like they, maybe you will have different opinions regarding this thing. Now let me give some options to make it easier for you. Let's say option 1 says that if I flip this coin over and over, I know my writing is quite bad, but yeah, over and over, roughly 50% will be heads. Now the second option says that head and tail are equally probable. Right? And the third third option says that both A and B make sense. Right? So these are the three options that you are having. Now, how would you interpret this thing that the probability of a head when we are flipping a coin is 0.5? So look at in the sorry. Yeah, sorry about that. So look at the very first option that we have, that if I flip this coin over and over, roughly 50% will be heads. Right? That's what we do in the frequentist approach. we repeat the experiment infinitely many times under identical conditions to see what is the relative frequency of that experiment. Okay, so this interpretation, what we are seeing in the first thing, that if we flip the coin over and over infinitely so many times, there are approximately 50% heads. So this is the interpretation when you will do, when you are doing this experiment, when you are doing a frequentist approach. Now, second thing, that is head and tails are equally probable. This is the interpretation that we usually give according to the Bayesian point of view. Okay, so basically both of the statements make sense, but the one is corresponding to frequentist approach and the second is corresponding to the Bayesian approach. So all the students who are, not all the students, I'm also a student, but yeah, all the ones who are watching this video, uh, if you have already studied the frequentist approach and all the procedures of it, then you must have known this, that while previously defining that a 50% of them will be heads, we always say that we are doing calculating the relative frequency corresponding to it. Okay, now what is actually the difference between them, that calculating the frequentist and calculating the Bayesian, that we will see when we will calculate the Bayesian questions. But yeah, what is the different what do the different I'm sorry, let's look at the basic differences between these two terms. Like, what does the probability mean when we are looking in the Bayesian? So in the Bayesian, a probability is, you can say, Bayesian measures the relative plausibility of an event. Plausibility of event. Okay, so relative plausibility means that it would be under some, pointing out some evidence, pointing out some facts, so it will be related to that. We will be considering some evidence and the facts when we are talking about Bayesian. So you can say in the probability, in Bayesian, the probability is interpreted as a measure of belief or uncertainty about an event. It measures the degree of belief or degree of likelihood that the event will happen, that the event will occur given the available evidence or given the available information. Okay, so in simple terms, we are just saying that Bayesian measures the relative plausibility of event. Now, when you are looking at the frequentist, the frequentist views frequentist. Yes. So, in simple terms, frequentist views the probability as the long run relative frequency of repeatable events. Okay, that's the very like simple definition you can say about the frequentist. So you can, if you want it to be more simplified, then the frequentist basically proportion of times an event would occur if an experiment were repeated infinitely many times under identical conditions. Under same conditions. Okay. So yeah, these are the two different views of them. Okay, these are the different point of views corresponding to them. So whenever you are having the events which are a one-time event, okay, whenever we are having a one-time event, now the frequentist approach definitely says that you need to repeat the experiment so many times to make the conclusion regarding it. Okay, so whenever you are having a one-time event, it would be better to go with the Bayesian point of view. Bayesian is more flexible here, like the events which are whether there will be a rain tomorrow or not. It is a one-time event, right? Now, similarly, whether a team would win a match or not. I've already discussed this one, that whenever a team would win a match or not, it's a one time event, because in the next match the team mostly the opponent team would be different. Maybe there are some players in the team that have been replaced, so the match would not be same, because frequentist clearly says that you have to perform the experiment under identical conditions. So in the next match, you will be not having the same conditions as you are having in this match. So in the one-time event, it is better to go with the Bayesian point of view. Now, what will be the procedure of this Bayesian process? I've already give a little brief about it, procedure of Bayesian. So the goal of them is basically same, to making an inference about an unknown quantity. We'll be having an unknown quantity and we want to make some inference regarding it. So making inference about some unknown quantity. Okay. For this, what are we having? Okay, for like what will be the inference procedure? So it is like before actually seeing the data, we have some prior information regarding that data. So that is prior probability. Okay, so from this prior information, when you will look this prior information in the broader view in more complex problems, we will be forming a prior model. Okay, so we are saying we will be having some prior probability or prior model. Okay, that is, let's say, probability of some hypothesis. Okay, now before collecting the data, we are having some information. Now the next step we are doing, we are collecting some data. Okay, after this you will collect some data. Okay, now after collecting data, we update our probability of hypothesis. That means the prior probability, we update our probability of hypothesis given the data we just observed. So that is said to be the posterior probability. And in the broader cases, as I have discussed, you will be having a posterior, we will be creating actually a posterior model, a posterior probability model and a posterior prior probability model. Okay, so here we are going to see the probability of hypothesis given the, I have already collected the data. Okay, so we are going to encounter these kinds of, that is basically a Bayesian procedure. You will be having some prior model and you will be collecting some data, and then you will update it to the posterior probability. Now for those, there is a just simple note point who have already studied the frequentist approach. So in the frequentist approach, if you have already studied it, there is a concept called a p-value. Okay, p-value. So when we are saying in frequentist, that is for frequentist. So in frequentist, p-value, what we have calculated, what is p-value? It is just simply the probability of observed data given the hypothesis H0 is true, right? So in the p-value, we actually calculate the probability of data given the hypothesis H0 is true. But look at here. Here we are calculating probability of hypothesis given the data. So don't get confused with these two terms. They are two different probabilities. Okay? Yes. Now, let's, this is just a simple note point. Now, let's look at this procedure of the Bayesian from a very basic Bayes rule. Okay, so I'm just going to consider it from the very basic, that Bayes rule for two events. Then after understanding the procedure for two events, we can generalize it for n number of events. Then we can go like more wider. We can generalize it for distributions, like going step by step. So Bayes rule for two events, let's say if you are having events A and B, then the posterior probability of B given A, that is, like, this is just a conditional probability, you can say that is A intersection B upon probability of A. Now we have already did this, that what is the simultaneous occurrence of two events when they are in the conditional probability. You can write down this as probability of B, probability of A given B, right? That is probability of B, probability of A given B upon probability of A. So here what we are having, this term is my posterior probability. Okay, probability of corresponding to event B. This is my prior information about the event, and probability of A given B is the likelihood, and this probability of A is actually my evidence. Yes, probability corresponding to some event A. So by the law of total probability, we can say this probability of A is probability of B into probability of A given B. I'm sorry about this, I don't know why this happens sometime. Plus probability of B bar, probability of A given B bar. Okay, this is my by the law of total probability. So what we are doing, we are having posterior, that is equal to prior into likelihood. Okay, and this evidence, which is also said to be the normalizing constant. Why, that I will tell you. Normalizing constant. Yeah, normalizing constant. Okay, so yes, this is what we are having. Now if you want to look into this like this, we are having two events B, we are having considering it for two events A and B. Okay, so this actually means, if you are looking into this one, that there is an event B and the complement corresponding to it, that is B bar. They are two disjoint events. Yeah, basically they are complement of each other, so they are being disjoint events, and this is my event A, which is occurring with both of them. That's what it means. Okay, so we are having A intersection B plus probability of A intersection B bar, and this is just the expansion of them. Okay, yes. Now let's try to understand it with some example if my pen works. Let's say if you are having suppose we wish to categorize an online news item as fake news or real news. Real news. Now, in fake news dataset, there are 150 articles posted on Facebook, and 60 of them are fake and rest are real. Okay, so what are we having? We are having the data of fake and real. So in this data set we are having 60 of the articles that are fake and 90 of the articles that are real, and so we are having a total of 150 articles. From these much are fake and these much are real. Now, assuming this is a representative sample, this could inform us our prior knowledge about how likely an article is to be fake news. So by just looking, this is my prior knowledge. Before collecting any observed data, I have not collected any data yet. We don't have any information regarding observed data yet. So yeah, before that we are having some prior knowledge that 60 articles are fake and 90 articles are real. So by just examining our prior knowledge, we can consider that if there is a new article that comes out, then it's more likely to have a real article, right? So now let's continue the question. Let's say in addition to this information of prior, we can observe. Now observe, that means we are having some observed data. Observe that 16 of the 60 identified fake news have exclamation points in headline. I sometimes write wrong spelling, but yeah, just understand them. Points in headline, and only 2 of 90 of real news have exclamation points in headline. Okay, now see it here. So we are having actually two pieces of information. Okay, what are these two pieces of information? So we are having two pieces of information. First is prior information. Now prior information is suggesting that 90 out of 150, that is 60% of articles are real. That means if there is a new article that is coming out to be, then I can consider that there is a 60% chance that it is a real article, right? So the new article is most likely to be real. Now, the new information which is after collecting the data, we are getting that the exclamation point, if you are looking through the data of exclamation point, then this data is suggesting that 16 of the 60 identified fake news. 16 of the 60 are identified fake news and 2 of 90 are real. That means this new data, observed data, is suggesting that the exclamation point data is more consistent with fake news. Okay, more consistent with fake news. So yeah, we are having two different informations, and from these two different information, we are getting some contradictory results. By just looking at the data, we have not calculated anything yet. So we need to balance out these two pieces of information, and that's very important in developing our conclusion, in getting our posterior understanding about the article, whether this new article that has come out, whether it is fake or not. Okay, so basically we are having our prior, and that is 40% of the articles are fake. We are having our data, which is and this data is suggesting that we will be having more common to fake news. That exclamation is point is used more in the fake news. Then we want to gather some information. We want to update our prior to posterior, that is the article fake or not. Is this new article fake or not, given that this new article uses an exclamation mark. Okay, so let's solve this problem with the help of Bayes rules. Okay, so for this, let's say consider some events, that we are having some event, let's say B. B is my event that a random news article is fake news, right? So the complement of it, B bar, that would be that a random news article is not a fake news. Okay, and we have already we already know the probabilities corresponding to it, that we are having the prior information that out of 150, 90 of the articles are real. That means we are having probability of that it being a real article is 90 out of 160, of it being a fake news, that is, I think, 60 out of 150. 60 out of 150. So that will be 0.4 and 0.6. Now this is based on prior model. Why am I saying this is a prior model? Because as I can see, this prior probability that we have framed for B and B complement, this is a valid prior model. Because for a prior model, if you remember, for a prior probability, for a prior probability function, what are the required things? That first thing, that it should account for all possible events. Okay, now yes, here we are accounting for all possible events, that articles will be fake or real. Account for all possible events. Second thing, sum of probability should be 1. Yes, here the sum of probability is coming out to be 1. Okay, and it actually assigns the probability to each of the events. Assigns probability to each event. So actually we are having a valid probability model here, which is my prior model we have framed. Okay, let me write valid probability model. Okay, yes, now consider our observable data. What is our observable data? The observable data suggests, let's say, consider an event A corresponding to it, that news items title has an exclamation mark. and the probabilities corresponding to it, that is probability that a new item that a news item has an exclamation mark, given that it is a fake news. These are 16 by 16. And probability that a news item has an exclamation mark, given that it's not a fake news, is 2 by 90. Okay, and that if I have already calculated, that is will be 0.2667 and this is 0.0222. Okay, so yes, this observable more of the fake news. Okay, now if A is my observed data, this is my observed data, that articles have an exclamation mark, then this means, so this is my event A, that the article is having an exclamation point. It can have the exclamation point when it is having a fake news and when it is having a real news. So we are actually calculating the probability of this new article having an exclamation mark, that is actually probability of A intersection B plus probability of A intersection B bar. Okay, now this is actually the law of total probability that we can expand. We have already discussed it, that this is probability of A given B, probability of B plus probability of A given B bar, probability of B bar. Okay, and we have already calculated the probability corresponding to it, probability of A given B bar, probability of B bar. Okay, so let's just put them. This is 0.2667. Probability of B is 0.4. This is 0.0222. 0.4 plus 0.0222, and probability of B bar is 0.6. 0.6. Let me just simply multiply them. Yes. Yes, so for the first one, we will be getting 0.101068 0.10668 plus 0.0222 into 6.6, that is 0.01332. Okay, which is summed up to be 0.12. That is the marginal corresponding to this event A. Okay, now what is our aim? We need to find out the posterior probability, right? That the article is fake given that it uses an exclamation point. That means we want to find out probability of B given A, which is equal to probability of A given B, probability of this event B upon probability of A. Now we just need to put the probabilities corresponding to each of them. We have already calculated it. So that is 0.2667, which is probability of A given B, probability of B upon probability of A, which is 0.12. And that is coming out to be, let me see. Yeah, if there is a calculation error, just let me know. 0.10668 upon 0.12 and 0.12, that will be 0.889. Now look what we are having. We were actually having the event B and B bar, and the prior corresponding to these events are that the probability that that a random news is a fake news, the probability corresponding to it was 0.4, and it is going to be a real news, the probability corresponding to it is 0.6. Okay, and the total is 1, right? Now, after considering the observed data, we are having the posterior probability, that the probability of this event, that a random news is going to be a fake news given the observed data, we are having the probability as 0.889, and by using the complement it will be 0.111, because post as prior probability is a prior model, it is a probability function. Similarly, posterior probability is also a probability function. Okay, it also satisfies the probability function properties, like sum of the probabilities 1 and all those things. But yeah, talking about the likelihood function, this is my likelihood function, this is not a probability model. Only these are the two things which are my probability models. Okay. Yes. Now, when we are studying the conditional probability, in that case, I have introduced one pointer there, that probability of A given B is always lesser than probability of A. That is true. That is true. But in under certain circumstances, you can have posterior probability, because as you can see, this is my probability corresponding to B, and this is probability of B given A. Here we are having probability of B given A, which is greater than probability of B, right? This is greater than this. And in the previous theorem we have studied, probability of B given A is going to be lesser than probability of B. But yeah, your conditional probability can also be greater than probability of that event B under some certain circumstances. Firstly, I'll just like give the brief introduction of this, like in what scenarios you can have a probability a conditional probability as greater than the unconditional probability, and then we will see the mathematical point of view. Okay, so consider some example. Let's say, so basically my I'm just trying to say that the certainty of the event B, it can might increase or decrease in the light of new evidence, in the light of new data. Okay, so it can happen in both the ways. You can have your conditional probability would increase, your conditional probability can decrease. Okay, so for example, if let's say, if you like any musical instrument, you practice it very on a regular basis. Let's say I like playing ukulele. Okay, so if I say that the probability of, because I let's say play ukulele every day, then probability of my ukulele, probability of ukulele, given that I practice it daily, given that I practice it daily, then the probability of me joining a ukulele program is more than the rest of the population. Than the rest of the population. Getting my point? Because I'm interested in this instrument, of ukulele, I practice it daily, then my probability of getting into the program, which is ukulele program, that is higher than the rest of the population, which is just the probability of ukulele, right? Now similarly, let's say if you are a health enthusiastic, that's a very good thing. But yeah, if you are a very enthusiastic, then you'll probably wash your hands on a very frequent basis, maybe 30-40 times or more than that in a day. Okay, so for a very health and enthusiastic person to get a flu is very rare chance. It's a very less likely to they are very less likely to get the flu. So probability of getting the flu for a very health enthusiastic person who actually wash their hands very frequently, that is lesser than the probability of the rest of the population who are getting, like they will get the flu, right? So depending on my data, that what kind of my data, what is the given information we will be having, it depends on that, like whether your posterior probability would increase or decrease. So in the light of new data, it can happen in both ways. So yeah, This case we have already discussed when we are talking about the conditional probability, that you can have posterior, that your conditional would be lesser than the unconditional probability. Now let's discuss about this case, that in mathematical terms, which is that particular case at that time your conditional probability would be greater than unconditional one. Yes, sometimes it just, some words are in my mind but I can't think of them. Yes, let's look at the note points of it. Okay, so we are saying, let's take a very new page. We are saying that probability of A given B is greater than probability of A if and only if we will be having probability of A given B greater than probability of A given B bar for probability of B or B bar greater than 0. Okay, now let's see how. My pen is leaking, so let's see. So we know that probability of B is equal to, basically probability of B bar is equal to 1 minus probability of B. I can write it in either ways also. Yeah, that's fine. And when we are looking at the unconditional probability of A, so by the law of total probability, we can expand it like probability of A given B, probability of B plus probability of A given B bar into probability of B bar. Okay, now we can rewrite this probability of B as 1 minus probability of B bar. I'm so sorry, my pen is very leaking today, but yeah, as I'm speaking I can see, like, assuming that you can understand it. Okay, and this will remain same, probability of A given B bar, probability of B bar. Okay, now taking probability of B bar common and firstly multiplying it with all the terms. So we are actually having probability of A given B minus probability of A given B, probability of B bar plus probability of A given B bar probability of B bar. Okay, taking common the terms of probability of B bar, let's write here probability of B bar, that would be probability of A given B minus probability of A given B bar equals to, I have also transferred them into this direction, so probability of A given B minus probability of A. So as you can generalize from there only, that this term, in this term you will be having probability of A given B greater than probability of A only if you will be having probability of A given B greater than probability of A given B bar. Okay, so that is the mathematical condition in which case you will be having your posterior probability greater than the unconditional probability, prior probability. Okay, so yeah, this is the Bayes theorem for two events, and we will be discussing the Bayes theorem in more detail. Firstly, the generalized case of it, then the Bayes theorem for future events, then the Bayes theorem for random variables. Okay, and going more into the Bayesians. Okay, so let's just go step by step. Okay, then let's meet in the another lecture. I hope you have a good learning in this class. Okay, bye.